So we're going to start off here with a little true or false. Okay, first statement. If a function is differentiable at a point, right, that means I can draw a tangent line to the curve and compute its slope. That's what differentiable means. I can find the derivative at that point. Then it must be continuous. True or false? Okay, and we did discuss this in class, that if there's an asymptote line, a jump, a hole, right, how could we possibly draw a tangent line to the curve when such a thing is occurring and compute the slope of a tangent line? Okay, so if we're differentiable, we have to be continuous. Okay, so then does that rule work the other way around? If I'm continuous, does that mean I can always take the derivative at any point at which my function is continuous? Okay, and for that, we have to look at some functions like this one. Okay, the absolute value of x, which has that sharp corner here. At this point of the sharp corner, this function would not be differentiable. Okay, because actually, you might not be used to seeing it written like this, but the absolute value function is a piecewise function, right? Y equals x, if x is 0, because it's got 1, 1, 2, 2, 3, 3, and then y equals negative x, if x is less than 0. Okay, so if we were looking at the slopes along this part of the curve, these slopes are always positive 1. Over here, these slopes are negative 1, right? And then by the time we get to 0, it changes to abruptly. Okay, we can't have that abrupt change in the derivative on the right-hand side and the left-hand side. Okay, if we tried to use the limit definition, we would see that the limit fails to exist because the limit from the left does not equal the limit from the right. Okay, so the derivative when x is greater than 0 is 1. The derivative when x is less than 0 is negative 1. Notice that even though this had the equal to sign, I no longer have that, right? Because I'm not differentiable at the point 0. Okay, so coming over here, this is the function y equals x to the 1/3, or the cubed root of x. The problem that we have in a function like this, although it's continuous, if I go to draw a tangent line to the curve, and I'm right here, right at 0, I would have a vertical line as my tangent line. And of course, we know a vertical line has an undefined slope. Okay, but if we went to our limit definition, which here it is, and so I'm saying that this is not differentiable at x equals 0. Everywhere else we're fine. Okay, everywhere other than 0. Same thing with this function. Everywhere other than 0, we can take the derivative. So if I plug in 0 plus h, right, that just ends up being h to the 1/3 over h. Okay, and then if I reduced that down, so remember how to, when you were in high school, or actually middle school, you did problems like this, x to the 6th over x squared, and how do you simplify? And you simplify by subtracting the exponents. Okay, so if I subtracted these exponents, I'd get h to the negative 2/3, so I'm going to keep that in the basement, right? And we've done a lot of work with what happens when the denominator gets very large, when we have a whole number in the numerator. If the denominator gets very large, then the fraction went to 0, right? But I'm sorry, this should be a 2/3. What happens when that denominator gets really, really small? Like I have one cookie and less people are coming to eat the cookie. Okay, or if you want to grab your calculator, do 1 divided by 0.000000001, hit enter. Your answer will probably be something in exponential notation because it will be a very large number. Okay, so as the denominator gets really small, the limit is infinity. Okay, because if you ask yourself, how can a limit fail to exist? Remember, that was the fine print in the limit definition. It said, use this definition to find the limit provided the limit exists. Okay, well, how do we get a limit that doesn't exist? When the limit is infinity, that's not a real number, or if we get different limits from the left and right hand side. So again, as I said, sharp corners, we can't take the derivative. Here's another sharp corner in this piecewise function. Often piecewise functions, even if they're continuous, if they meet at a sharp corner, then the function's not differentiable at that meeting point. All right, and another function, this is on our lab, x to the 2/3, we get what's called a cusp. Okay, ooh, that's sort of nasty drawing. That should be totally symmetric with respect to the y-axis, okay? But this was on your lab, so you've seen this function before. And therefore, when we come down here and we do our true and false, just because a function is continuous at a point doesn't mean it's differentiable at that point. So that would be a false. When we look at functions that are always differentiable, right? What's always differentiable of our favorite friends as far as the functions, okay? And polynomials are always differentiable, no matter what, because they're nice, smooth, flowing curves. Sine and cosine are differentiable everywhere. That's all I can think of as far as generalizations, because other functions we have to watch for discontinuities, or as we just saw, we have to watch for sharp corners or cusps or vertical tangent line.